Lesson 117. In this lesson, we're going to look at some applications of the Moivre's theorem and how it can be combined with trig formulae to solve certain types of problems. Here is example 1. Develop a formula for cosine 3 theta in terms of cos theta. So when I look at cos 3 theta, it kind of reminds me of, a power of a complex number that will give me some kind of a form like cosine n theta plus I sine n theta. So what I'm going to do is I'm going to let z to be cosine theta plus I sine theta, or write that in polar form, which is cis theta, and try to raise z to the power of 3 in two ways. First, using the Moivre's theorem and polar form, and then compare that to, the cube of z in rectangular form. So if I do this first, this is going to give me cis 3 theta, which is cosine 3 theta, plus I sine 3 theta. And this is based on the Moivre's theorem. Okay, and then I'm going to do the same thing, similar, but this time to expand cosine theta plus I sine theta to the power of 3. I'm going to use binomial theorem to expand this. So I know that power of 3 refers to the 3 choose our row in Pascal's triangle, which is 1, 3, 3, 1 for the coefficients. So I have cos 3 theta plus 3 cos squared theta I sine theta plus 3 cos theta I sine theta squared plus I sine theta cubed. Okay, and then if I simplify those powers of I can also make use of this relation. I is here, I squared is -1, I cubed, I to the power 4, and so on like that. If I go around that unit circle, then I know that every other term I'm going to get a real part, and every other term here I'm going to get an imaginary part. So let's group cos cubed theta, and then I squared is negative, so minus 3 cos theta sine square theta. That's the real part. And then factorial I have 3 cos square theta sine theta. And then from the last term, I cubed would be negative I. So minus sine cubed theta like that. Okay. So now I have two versions of z to the power of 3. This is using binomial, which means that if I want an expression of cos of 3 theta in terms of cos theta, I can set the real parts to be the same thing. Okay, so I have cos 3 theta equals to cos cubed minus 3 cos sine square. I want the whole thing in terms of cosine only, which means that I can rewrite sine squared theta using 1 minus cos squared. Okay, a trig identity. And so this is cos cubed minus 3 cos theta times negative cos squared theta. That gives me plus 4 cos squared cubed. So all together. And then minus 3 cos theta. Okay. Let's take a look at example 2. So here we're going to simplify the expression cos 9 theta plus I sine 9 theta over cos 2 theta plus I sine 2 theta times cos 3 theta plus I sine 3 theta. You notice that if the argument matches in a cos plus I sine expression, that really represents, you know, a complex number. If I write the top number, complex number in polar form, this is really cis 9 theta. In the denominator, I have cis 2 theta multiplied by cis 3 theta. So we can continue to use the Moivre's theorem to represent these as powers of complex number. This is really cis theta to the power of 9 cis theta squared times cis theta cubed, right? So using exponent laws now, the multiplication here gives me cis to theta to the power of 5, and then dividing 2 powers, I have cis theta to the power of 4. And then if we bring it back to rectangular form, just like how the question was expressed in, this really is cis 4 theta or cosine 4 theta plus I sine 4 theta. All right. Here is example 3. In this example, we're actually going to develop some property of powers of complex numbers that can be useful in, you know, a grander scheme of things afterwards. But let's start by letting z to be, you know, a basic complex number with modulus 1, argument theta. It's written in the form of cis theta. So z to the power of n would be cis theta to the power of n, or cis of n theta, which in rectangular form is cosine n theta plus I sine n theta. Okay. If we have z to the power of negative n, in other words, this is also 1 over z to the power of n. Keep that in mind. But we're going to develop the idea based on the negative n power of cis theta. This is cis of negative theta, which gives me cos negative n theta plus I sine negative n theta. But you may notice that, you know, if theta and cosine negative n theta is equivalent to cosine n theta, sine n theta and sine minus n theta have a negative relationship. So this is negative I sine positive n theta. Okay, so that's using trig identities. So why is this important? Because now we're going to apply these expressions in C, where we're going to add z to the power of n plus 1 over z to the power of n. Okay, and see what this gives us. So z to the power of n, we found that to be cos n theta plus I sine n theta. 1 over z to the power of n, so z to the power of negative n, we found that to be cosine n theta minus I sine n theta. So it turns out that this is 2 times the real parts. Okay, and I'm going to rewrite this and put a box around this expression just because it is useful. Now, what if we subtract these two expressions? What is that going to give us? Let's see. We have cos plus I sine, okay, minus cos. Now, minus negative I sine, so minus plus I. So this time we are canceling out the real part, but we have doubled of the imaginary parts. So this is z to the power of n minus 1 over z to the power of n. Okay, let's see why these are useful later in the next example. Okay, so here we go. Using the results in example 3, let's find the cube of cosine theta in terms of first powers of the cosine function. So cosine cubed can be related to this because cosine talks about the real part. Right? So now if I let n to be 1 so that we will have cosine theta in the expression, then I'm going to have z to the power of 1 plus 1 over z cubed, like that. Okay. In other words, if I expand the left side of this expression using binomial theorem, okay, this is 8 cos cubed theta, and then do some grouping right here. If I simplify these powers of z, so this is really z, 3z, this is 1 over z, and then regroup these terms, the first term with the last term, and then the middle two terms, and factor out 3, I have z plus 1 over z. What do you notice? These are expressions that we're familiar with, right? Z cubed plus 1 over z cubed is 2 cos 3 theta plus, this is 3 times z plus 1 over z is 2 cos 1 theta. As a result, cosine cubed theta is 1 over 8 times 2 cos 3 theta plus 6 cos theta, or 1 over 4 cos 3 theta plus 3 over 4 cosine theta, just like that. Okay. Hence, find the integral of cosine cubed x dx. What have we got here then? Instead of saying this is cos cubed x dx, I now have a new expression of 1 over 4 cos 3x plus 3 over 4 cos x dx, which I can integrate these one term at a time. So cos 3x has an integral of sine 3x over 3. Multiply that by 1 over 4, I get 1 over 12 sine 3x. And then for cos x, I know the integral is sine x. Multiply that by 3 over 4 plus c, and we're done.